I'm Nathan Hostetler. I'm a third-year student in neuroscience at Western University, and this presentation is on adaptive procedures that control the false discovery rate. So it's a way to correct for multiple comparisons. All right, so if you're watching this video, you probably already know, but correcting for multiple comparisons is necessary because when you run a large number of statistical tests, there's always a chance that some of them are going to come back as having found a significant effect, even if there is no effect, so you'll get a false positive. So if you're going to run a large amount of tests, you should correct for the fact that you're running a large amount of tests, so that's correction for multiple comparisons. It's basically just saying we're acknowledging that there's a chance that there's going to be false positives because we're running so many tests, and we're making our criteria for significance more stringent to avoid having too much false positives. So why did we do it in our study? So the study that I'm involved with was investigating the surface area, volume, and thickness correlates throughout the brain with a variety of different measures of aggression and callous and emotional traits. So you can imagine those three measures of brain size and all of these measures of aggression and callous and emotional traits. We were doing a lot of comparisons, so it was necessary for us to correct for multiple comparisons. However, there's a few different ways that you can correct for multiple comparisons, so I'll go over a few of them. You could correct for the family-wise error rate. So the family-wise error rate is the probability of coming to at least one false conclusion in a series of hypothesis tests. And an example of a procedure that corrects the family-wise error rate is the Bonferroni correction, but this procedure is criticized because it's not very powerful, so there's a good chance you'll make a type 2 error, which is failing to detect a significant difference when it is there. So another option is to correct for the false discovery rate. And in contrast, whereas the family-wise error rate is the probability of coming to at least one false conclusion in all of your tests, the false discovery rate is the expected proportion of false positives among your positive tests, if that makes sense, if that distinction makes sense. So an example of how you would correct for the false discovery rate is the Benjamini and Hochberg procedure. And a positive of this is that it's much more powerful than the family-wise error rates, so you're less likely to commit a type 2 error, sorry. So I've included this graph here just because it shows the relative powers of these different procedures. So if you see this Bonferroni procedure here, let me get a pointer. If you see the Bonferroni procedure right here, that gold, so that's one that corrects for the family-wise error rate, whereas this BH procedure, that stands for Benjamini and Hochberg, and that's one that corrects for the false discovery rate. And you can see consistently that this purple procedure here is much more powerful. It has smaller p-values, so you're less likely to commit a type 2 error. Okay, so how are you going to do this Benjamini and Hochberg procedure to correct for the false discovery rate? So this is just an example of some raw data that I had in my study. So the first thing that you want to do, you want to rank the p-values in ascending order. So you can see 0.02 is less than 0.023, yada, yada, yada. And now that you have the rank, you go on to the next step. So you need to calculate this value right here. I is the rank, so for instance, number 1. And then Q is the desired false discovery rate. This is typically set at 0.05, but sometimes you'll see it set at 0.1. Kind of pick your battles. And M is the total number of tests, so in this case, it's 3. So to calculate for this first row, for example, I would do 1, because that's I, times Q. So that was 0.05, that was my desired false discovery rate. So 1 times 0.05 divided by M, which is the number of tests, which is 3. And then the criteria for significance, you want to compare this calculated value to your observed p-value. And you're looking for an instance where the observed p-value is less than this calculated value of IQ divided by M. And not only that, once you find a value where the p-value is less than IQ divided by M, all p-values less than this one are significant, regardless of if those p-values are less than their calculated values of IQ divided by M. So you can see, in this case, this p-value is greater than its value of IQ divided by M. So you move on to the next test, and you do the same thing, IQ divided by M, and you see that this p-value is less than the calculated value, IQ divided by M. So this reaches the criteria for significance, and then so does this first test now, because it has a lower p-value. So the highest p-value for which p is less than the calculated value of IQ divided by m, and any p-value smaller than that reaches the criteria for significance. So to summarize, you're going to rank your p-values from smallest to largest, calculate the IQ divided by m for each p-value, where I is its rank, q is your desired false discovery rate, usually 0.05, and m is the total number of tests. And then choose the largest p-value for which p is less than the calculated value IQ divided by m. All p-values smaller than this value will be significant, regardless of if those p-values are smaller than their calculated values of IQ divided by m. Alright, so the procedure I just went over is actually not ideal. It's too conservative in a number of circumstances, which means it could be more powerful. And so that's why we need something new. Despite the fact that that test that I just went over is very heavily cited and it's established in the literature, there's actually a better way to do it. So this kind of summarizes what I just said. When some of the null hypotheses are not true, in other words, when you have some significant effects, the procedure I just went over is conservative by a factor which is the proportion m0 divided by m of the true null hypotheses among the hypotheses. So it's conservative by the true null hypotheses divided by the total number of hypotheses. So if you have a lot of significance, then you're going to have a relatively small fraction of true null hypotheses amongst your total hypotheses, and this test is going to be way too conservative. I hope that makes sense. So yeah, when you tell the previous procedure to correct at a false discovery rate q, it is actually correcting at a false discovery rate of q times m0 divided by m. And that's problematic because m0, the number of true null hypotheses, will inevitably be smaller than m, the number of total hypotheses. So if you're doing m0 divided by m, it's a smaller number divided by a bigger number. So you're multiplying q by something that's less than 1. So you're making your q excessively too small. So you're thinking that you're correcting at your q, which you've set to 0.05 or whatever. But actually, because this test has some problems, you're correcting at a level smaller than q. So you're being too stringent. So yeah, this really just summarizes what I just said. So the general idea of the new procedure is that you're going to do the old procedure to estimate the value of m0, which is what I mentioned on the previous slide. And once you have that value estimated, you'll be able to reestablish a new q value that's going to be more accurate. So yeah, in light of this m0 that you've just figured out, calculate a new level q. So you're going to calculate q prime, which is your old q. So in my case, it was 0.05 times m divided by m0. And you'll notice that that kind of makes sense because if your old q value was conservative by a factor of m0 divided by m, and now you've figured out what m0 is, and you multiply that q value by m divided by m0, those fractions are going to cancel out and you're going to be left with just that perfect q value. So yeah, that's really the logic behind this. And yeah, not only is it less conservative and more powerful, it's actually it's doing a better job. It's correcting at the false discovery rate that you set more precisely than the previous procedure. So it's not like this is some reckless procedure that's just trying to find significance at the expense of accuracy. It is actually more accurate than the previous test. Okay, so there's a number of different procedures that do what I just outlined. That is, they try to find a new value, q prime, that's going to be more accurate. So I just used one of them. I'll link a paper in the description that has a lot of these different methods. So the basics, you're going to use the linear step-up procedure, and that's the procedure that I outlined earlier in the video with an example. And you're going to do it at level q prime. So that's going to be your desired level q, so it would be 0.05 divided by 1 plus q, so 0.05 divided by 1.05. So you just do that completely normal, just like the example I previously did, just with your new value q prime. And then let R1 be the number of rejected hypotheses. So yeah, that's kind of the first step. I'll move on now. So this is our raw data. Again, we're going to rank them. Next, we're going to calculate IQ divided by m. So rank times q divided by m. But remember in this instance that our q is going to be right here, q prime. So it's going to be our actual q, 0.05 divided by 1 plus q. So that's why in this column, I'm using q equals the q that I actually desire, so 0.05, divided by 1 plus 0.05. And you'll see, let's see, this p-value right here, 0.011, is less than 0.015. So this reaches the criteria for significance, and so does this test, because this test is this has a smaller p-value than this test. So even though this p-value is greater than the calculated value of IQ divided by m, because the p-value below it is smaller than its value of IQ divided by m, both of these are significant. So now, if we go back to here, let R1 be the number of rejected hypotheses. We have 2. So 2 hypotheses rejected, therefore R1 equals 2. And then look right here, let M0 equal M minus R1. M is the total number of tests, so 6. So we have 6 minus 2, M0. M0 equals 4, that makes sense. And then now you do the same linear step-up procedure with Q star. So that's going to be Q prime. So recall that Q prime is right here, Q divided by 1 plus Q times M divided by M0. M is going to be 6. M0 is going to be 4. We just found that out. And now when we do this, we have these new calculated values of IQ divided by M that are going to be less conservative and more accurate. So in our case, it actually didn't make a difference, but you can see here, if you compare these critical values, how it would have made a difference, because say that this p-value was 0.032, with this first step, it would not have been significant because the p-value is greater than that. But with this second step, it would have been significant. So this two-step procedure catches more than the one-step procedures, and it's more powerful. So to summarize, we went over why you should correct for multiple comparisons. We discussed the false discovery rate, which typically is more powerful than procedures that control for the family-wise error rate. And then we discussed the old methods of correcting for the false discovery rate. So that was the original procedure by Benjamini and Hochberg, and the new methods, which are the two-step procedures that first try to calculate that value M0, then use that value M0 to correct and get a new Q value that's going to be more accurate. So they are not only more powerful, but they're also more accurate, and that's important to keep in mind. It's not just like a reckless procedure that we're doing just because we want to see significance. It's a procedure that we're doing because it just does a better job at correcting the false discovery rate that we wanted to correct at. And then we went through some examples. So I hope that was clear, and if it's not, feel free to leave a comment, and I would be happy to address it. And then I've also put a Google Drive link in the description. It has the annotated PDF that I made of the paper. So just while I was reading the paper that was outlining all these procedures, I was kind of writing comments. So it might help you follow along with the paper. And it contains this presentation as well. And then it contains a link to this website, which I found helpful.